Oops. Okay, I think this is how I wanted it to be. Sorry, it's taken me a second to figure out the two screens because I'm presenting from my desktop and then I'm also, um, you know, like using the audio for my iPad because my mic sucks. But anywho, um, so this is my application study one, and it is going to be just me presenting. But yeah, let's get into it. So, an introduction. So, based off of, what was taught in lecture, we have the quote that extreme seeking control is a control algorithm that uses online estimation and optimization to find extrema of a system in a model-free manner. Okay? And then, as we know, this can be done for single inputs or for multiple inputs. And this can be used basically for anything that requires optimization. I think some of the examples presented in the problem statement was like braking and fuel consumption, or like calculating the perfect position of, a solar panel to maximize power, that type of stuff. So we will also be using this for the problem that I will present. So since it is just me and I'm undergrad, I decided to do a single input problem, which of course has to be unconstrained. So just a little bit of background and relevance. So I also decided to take the solar panel route that seemed the most interesting to me. Um, the problem that I tried to solve was I did a little research and I noticed that sales of solar panels are declining in certain parts of the US. And so I decided that I wanted to do a problem that kind of like um, does a units versus profits, um, tests. And that's especially because, money talks. So we want to see the profits. How many units do we need to maximize our profits? So why is this important? Um, so reduced emissions, so using renewable energy like sunlight and wind and stuff like that, has been shown to improve public health, obviously, because we're not having as much air pollution. The environmental aspect also kind of ties into this. We want to encourage people to use renewable energy more because, leading into the next point, fossil fuels are finite and renewable energy is not. One day we're probably going to run out of fossil fuels and maybe we'll go to Mars and try and dig up their stuff there or whatever. But at the end of the day, like the sun is always going to shine, the wind is always going to blow. So we definitely want to aim to use renewable energy. And by using renewable energy, we can mitigate climate change and its effects, especially because it is expensive to repair damaged homes, schools, buildings in general, roads, everything else from frequent natural disasters in general, but definitely if they're more frequent. So, and then we also want to be able to lower energy costs through, the use of um, a more, a less finite source. So, leading into our problem statement, we're trying to sell more solar panels, but people are not easily persuaded to buy them. Let's say they have issues like, oh, they're ugly and this, that, and the other thing. And as we said before, money talks. So we want to develop a model that can show the maximum amount of solar panel units that need to be sold to maximize the return of investment. Profit relationship. We're assuming that this is solely dependent on the number of panels used. In the next slide, I'll kind of talk about the other factors and quote unquote underlying physics of this task. But yeah, and this is a very simplified problem just for the sake of showing the system that was created to help find our extrema. But yeah, so as you can see on the right, I generated an equation that describes the profit based off of the number of panels sold. So we have money generated minus our expenses. And in total, we get this equation at the bottom in red, which is negative 2x squared plus 6,700x minus 5,000 is going to give us our overall profit of this adventure. So our key underlying physics. So in this problem, as I've done it, is it technically doesn't involve the underlying physics aspect of this. It's just saying the number of units sold is going to show us a profit. But as we know in the real world, it's not as linear, or, our equation isn't linear, but it's not a direct one-to-one effect, if you will. So there's going to be a lot of other factors involved, which is the sunlight intensity, shade, temperature, where this person is located, obviously, because some places get more sunlight than others, where the panels are located on the roof or wherever these are placed. Obviously, the angle is going to matter because if it's faced toward, the maximum intensity of sunlight, then that is going to obviously maximize the power output. And then we also have things like battery storage that can affect this as well. And another thing to consider is the fact that, like, this model is assuming that every single day, maybe the power output is going to be the same. So obviously this would vary on a day-to-day basis in real life. So yeah. So our optimization objectives. So the way that I formulated this, I'll kind of work backwards here and start with the optimization statement on our right, which shows that we're trying to maximize X, which, represents the number of panels sold. We want to maximize X given the function, but then we put it into negative null form, which means that we want to minimize X and change the signs within our function to make it fit. And so the way that this is an unconstrained problem is because I didn't put any constraints on X. So we assume that, we had infinite amount of money to like invest. We had infinite space. So if we get some absurd number later on, obviously it's not going to represent like one home, or maybe it could, but it might be like more than one home, definitely. Um, yeah, and so things like space and money would introduce unit constraints. Yeah, so we would have to say like, oh, because we have X amount of yard space, the absolute maximum number of panels that we could fit in the yard and on the roof would say that like the X that X is subject to the constraint of like it has to be less than or equal to whatever the max amount of units we could fit into that space would be. But we're not limiting this, so it's probably going to be some insane number. And yeah, so as I said before, we're saying that the panels are uniform and they generate the same amount of energy every day, etc. And the optimization objective is that we want to maximize um, the overall profit, which is going to come from maximizing the units, most likely. So yeah, we want to maximize the number of units that we're having. So I'm going to switch my screen. And we're gonna, okay. So here we are in Simulink. We have the plant model, which will um, kind of like help show us what, um, the maximum number of units and the maximum profit based off of this kind of like shuffling our feet and estimating, um, you know, set of procedures. And so coming over here, you can see that we have our gain, and I'll kind of go into what the specific values were used in a second. But then next you have your gradient ascent, and then we have a scope over here to show the number of units. We have our plant, we have our profits, we have our high pass filter. We're multiplying things. We have our low pass filter, gradient estimation, and our dither. So if we zoom in here, we can see what our plant looks like. So we have X being multiplied by 2. Yep. And we're multiplying that. And then we have our 6,700 gain here to represent the 6,700x. And then we have the 5,000 constant. And we're going to get our profit. Basically, taking that equation that we saw earlier and putting it into some sort of plan. So when we zoom back out, back to our original plant, so I just want to like look at some of these numbers. Obviously, this is like the very plain form of this. Over here, we would have like a 1 and then a 1 over here as well. And some of these numbers are changed a smidge. So in order to tune it, because here, let me just show you the graph that we get now. It looks very smooth. Over here in this region, if you look really close, you can see that it's very very scary looking. There, it like goes up and it goes down, up, down, and then it starts to level out. And so, in order to like make this look better, we had to change the gain. So our gain over here is going to be 0.008. It started at like, I think I want to say like 1, and that like it became infinite, and it was crashing, maybe not crashing, but it was popping up errors down here in this diagnostic viewer. But if you play with that more, then you'll be able to have like a more finite result. And then to kind of like change the resolution and stuff like that, we changed this value to 4 and this value to 0.5. Once again, it was basically like trial and error. Like you add a number here. Once we like sorted out the gain, once I sorted out the gain, that was one of the biggest things, because then it started to look like a smoother curve. But yeah, then you have to play with the high pass filter and the low pass filter. So that's how I tuned it. Like, it was a lot of trial and error, basically. Yeah, and if you have a gain that's too high, then it's going to make your thing blow up and, like I said, become like infinite. So we had to make the gain very, very, very tiny to make it look reasonable. And then if you look up here, you'll see that our time is kind of large, but that's also to kind of help see the bigger picture over time, because it looks crazy in the beginning stages of the output. So yeah, coming back to this, so this is our number of units graph. As we can see, it looks a little scary here, but it forms a really nice curve that starts to plateau around 16,000. So maybe like a little bit above that, but really close to 1600, sorry. And then for our profits graph, we have it going up over um, 5 times 10 to the 6. It looks like it levels out at about 5.5 times 10 to the 6. And soon we'll get into all of that and, if this is what we expected or not. But as you can see, it forms a nice curve and it plateaus at these, values that we can see. Oh, I just realized this whole time you can't see these pop-ups. Oh, brother. Okay, let me change that. Um, Maybe I'll just change it to the screen share. Okay. There we go. I should have did this the whole time. Sorry about that, but as you can see, like it gets a little scary and then, over here in the beginning, we had to tune and now that was fixed. Because it was only showing this part. So we had to increase the time and then we had to play around with the gain and the low pass filter and the high pass filter. So we get that the maximum number of units to maximize profits is going to be around 1600. And then over here with our profits, it's going to be around 5.5 times 10 to the 6. Very sorry. The fact that you couldn't see this until now. All right. So now we can kind of go back. So yeah, we talked about how I tuned it. Once again, it was a lot of trial and error, but we made it through. And then yeah, we know that like if the gain is a little bit too high, then the thing will blow up and be infinite. So reflection, was I happy about the results? Yes. Why or why not? So when calculated by hand, we get that 1675 units is where the maximum is, and then it's 5.6 times 10 to the 6 in dollars in profit. And if we bring up our model again, we can see that that's exactly what we get over here, right? So it's 1600, a little bit over. And then profits, it's about 5.5 times 10 to the 6. Another thing that we can do is come over here to our graphing calculator, and we can see that this is going to be the red is our original function. We see that it has a max at 1675 in units and 5.6 times 10 to the 6 in dollars in profit. So, yes, this was very good results. And yeah.